So I like to call this lecture the lecture on summations, or more simply put, fancy addition. Now, keep in mind, we have done fancy addition, or at least compressed addition, for a while now, right? Ever since about the third grade. If I asked you to do 2 plus 2 plus 2 plus 2 plus 2 plus 2 14 times, we have a way of doing that quickly. We just write it as 14 times of 2, and we all know that to be 28. But we learned that when we were first learning about multiplication by literally counting 2 at a time. 2 and 2 was 4, up 2 more made 6, up 2 more made 8, up 2 more made 10, and then we kept track on our fingers until we had hit 14 repetitions of 2. And then we learned our times tables, and many of us forgot that the way we were first introduced to multiplication was through addition. What we're going to explore in this class is there a similar way for me to express other addition problems, maybe addition problems that don't just use a single number over and over and over again? Now, keep in mind, this lesson is one of the first ones that's going to get quite dense. Has a lot of formulas. It has a lot of proofs. I'm going to show you a number of pictures that help make sense of those, but I would strongly recommend that you print off the guided notes, that you go back through it, because the purpose of my lecture, any given time, I'm not trusting that I am teaching you, right? That would be too false of an assumption, because statistically and scientifically, it's pretty much assured you're going to forget most of what I say by the time the hour is over. That happens regardless in any class. So what I'm trying to give you in these lectures is a jumping off point. I'm trying to get you comfortable with the idea. If I can have you leave the class and you go, okay, I think I got that, that's good. Because then when you look over the guided notes, they're not so dense, they're not so intimidating, and it's easier to pick out those refresh items from it. Versus if I asked you all to go teach yourself calculus from a textbook, that would be challenging, because you would have to be looking through dense representations of material for the first time, and then also trying to understand it. That's too much. But it's pretty easy to look at textbooks once you know what they're talking about. That's kind of what the guided notes are provided for. They're trying to provide you with a reference that you can look at after you have a level of comfort with the material. So this lecture is about trying to give you comfort with the material. For the density and for the formality, go look at the guided notes. It will help to anchor out a lot of those details. So let's begin with a motivation, a historical motivation, if you will. This is Carl Friedrich Gauss. Legend has it that Carl was sitting in his 7 years old, sitting in his elementary school classroom, and he is daydreaming, looking outside of the window and not paying attention to the teacher. The teacher is upset by this and comes up to Gauss and says, to punish you, I am going to ask you to add up all of the numbers between 1 and 100. That will be a painful exercise and will teach you to daydream in my class. And she asked Carl to go up to the front of the room and write on the chalkboard all of his work. But within seconds of being asked to do this, Carl looks at his teacher and says, the answer is 5,050. Now, was this child a genius, a supercomputer of a human? The teacher definitely didn't believe so. The teacher thought that Carl was making the answer up, punished Carl more severely, went back to her desk and found out that he was right. So the question is, how did it happen? Well, the creative approach is that it was a creative approach. Instead of trying to brute force this problem, where you go from left to right and start adding from small to big, there can be insight if instead you allow yourself to recognize the patterns. Because hidden within this is bunch of different pairs that all pair up to make 100. 2 would partner up with 98 to make 100, 3 with 97. So a quick question for you all in the chat, how many pairs existed in this that would create 100? How many 100 creating pairs are there? We might think 50, but what's 50 partner with? All right, there we go. It's 49 of them, right? Because you can think of it, every number up to 49 has a complement If you flip it around 50, it has a complement that it will partner with, right? 1's going to partner up with 99, 49 is going to partner up with 51, 50 in the middle is left unpartnered. So we have 49 times of 100 caused by our pairing. Oh, scratch that. There's 100 right here. So 50 pairs of 100 that are present and one lone 50 in the middle. Well, 50 pairs of 100 is 5,000 and a lone 50 makes it 50-50. Quick, nice, patterned, creative. So this is the approach that we start to recognize that there might be hidden and interesting insights and patterns within this patterned addition, right? Because multiplication would not work for this. I don't have a repetition of the same thing many times. We need to look for different creative approaches. Now, although I like to use the story here of Carl Friedrich Gauss, in truth, the equations that we will be using in this lecture were first discovered by the algebraists of India and Iraq. So do give credit where credit is due. These are equations that came out of the Middle East and India, as they were the ones who were exploring algebra when most of the Western world was exploring geometry. So these are equations that were known way before Gauss. But Gauss has a fun story, so I like to share it. Now, let's talk about some other patterned addition. For example, the square numbers. You may all know them. 1 squared, 2 squared, 3 squared makes 9, 5 squared makes 25. But have you ever noticed that the square numbers are actually patterned addition? That 1 is 1, sure, but 4 is 1 plus 3. And 9 is 1 plus 3 plus 5. And that 16 is 1 plus 3 plus 5 plus 7. So in fact, the square numbers also can be reached by adding up all of the odds. So if you want to know the fifth square number is the sum of the first 5 odd numbers. And we can see that in this picture, right? First odd number, second odd number, third odd number, fourth odd number, fifth odd number. So we have the square numbers. The square numbers have hidden patterns of addition within them. On top of that, what about other shapes, like the triangular numbers? There are triangular numbers, the numbers that can be formed into triangles. These also have patterned addition. 1 and 1 plus 2 makes 3. And then 1 plus 2 plus 3 makes 6. 1 plus 2 plus 3 plus 4 makes 10, and so on and so forth. There's patterned addition within shapes of these numbers. Square numbers are not the only shaped numbers. What about pentagonal numbers? There are pentagonal numbers, numbers where you can make a pentagon, and they have patterned addition within them as well. 1, then 1 plus 5, 1 plus 5 plus 10, 1 plus 5 plus 10 plus 15, we see the pattern. So we have patterned addition that occurs when we're talking about things where we might not have expected to see it. Patterned addition. Let's do a fun little thing here. Take a look at this shape, this progression, this pattern. Now you might see that there are more blocks in case 2 than case 1. And you might see there are more blocks in case 3 than case 2. Think to yourself for a moment, which blocks are the new ones? All right, so maybe you see this where these 4 blocks are represented on the side, and you've stacked more to the right of them. Maybe they're in the center and you've stacked more on top. Maybe they're off to the right-hand side. Maybe they're on the top. Like, find out where is it for you, because it might not be the same thing for the person sitting next to you. And to kind of make that demonstrated, let's take a look at a little abbreviation, a little story to go along with that. This is one of my favorite math education researchers. Her name is Jo Boaler. She teaches out of Stanford and is constantly giving me many interesting ideas for how different perspectives in math can often allow for us to see these patterned relationships between equations. No, hold on, I don't think I'm sharing the audio with you. Let's try that again.
Difficult to have a growth mindset in maths if you're constantly given short, closed questions that you get right or wrong. Those questions themselves transmit fixed messages about math, that you can do it or you can't. So we have to open up maths questions so that there's space inside them for learning. And I want to give you an example now. We're actually going to ask you to think about some maths with me. So this is a fairly typical problem that's given out in schools, and I want you to think about it a bit differently. So we have 3 cases of squares. And in case 2, there's more squares than in case 1, and in case 3, there's even more. And often this is given out with the question, how many squares would there be in case 100 or case n? But I want you to think of a different question now. I want you to think without any numbers at all, or without any algebra. I want you to think entirely visually, and I want you to think about, where do you see the extra squares? If there are more squares in case 2 than case 1, where are they? So if we were in a classroom, I'd give you a long time to think about this, but in the interest of time, I'm going to show you some different ways people think about this. And I've given this problem to many different people. And I think it was my undergrads at Stanford who said to me, or one of them said to me, oh, I see it like raindrops, where raindrops come down on the top. So it's like an outer layer that grows new each time. It was also my undergrads who said, oh no, I see it more like a bowling alley. You get an extra row, like a row of Skittles that comes in at the bottom. Very different way of seeing the growth. It was a teacher, I remember, who said to me, it was like a volcano. The center goes up and then the lava comes out. It was another teacher who said, oh no, it's like the parting of the Red Sea. The shape separates and there's a duplication with an extra center. And I remember this this one as well. Some people see it as triangles. They see the outside growing as an outside triangle. And then it was a teacher in New Mexico who said to me, oh, it's like Wayne's World. Stairway to heaven, access denied. And then we have this way of seeing it. If you move the squares, which you always can, and you rearrange the shape a bit, you'll see that it actually grows as squares. So this is what I want to illustrate with this question. When it's given out in maths classrooms, and this isn't the worst of questions, it's given out with a question of how many. And kids count. So they'll say in the first case there's 4, in the second there's 9. They might stare at that column of numbers for a long time and say, if you add 1 to the case number each time and square it, then you get the total number of squares. But when we give it to students and teachers, high school teachers, and I'll say to them when they've done this, so why is that squared, do you think? Why do you see that squared function? They'll say, no idea. So this is why it's squared. The function grows as a square, and you see that squaring in the algebraic representation. So when we give these problems to students, we give them the visual question. We ask them how they see it. They have these rich discussions, and they also reach deeper understandings about a really important part of mathematics.
So I like to show that video because it shows not only that there are many different opinions, many equally valid perspectives in mathematics, which is useful. If you all have seen in the week 0 material, then you saw one of my favorite lectures there where they are talking about that math is a place to practice empathy, where we're trying to understand different perspectives. This is a good case of that. It also helps us to recognize that the stress should not always be on the correct answer, but should instead be on the method of approach and the explanation that is most creative. That there are values in that. And we're going to see that today, that it helps us to discover some very insightful formulas and equations. All right. So let's go ahead and take a look here. These were some of the different ideas, the perspectives that were held in that video, right? We have the raindrops from on top and the bowling alley from below and this overflow of lava going to the sides. If you look at them figure by figure, you can make a pattern out of that, right? Where we start off with 4 things, and then we add on top of that 5 things, and then we add on top of that 7 things. So maybe the 3 things actually came from 3 on top of that center block, where it's 1 and then 3 on top of that, then 5 on top of that, and then 7 on top of that. So we can look at this progression as if it's the sum of the odd numbers. But we could also look at it as if it is something where there are triangular numbers, right? Where if you have that spreading and that duplicating, we have the triangular numbers, where on either side we have the triangles, and then we have a certain amount in the middle. So we have the triangular numbers because we're forming triangles on both sides. And then we have the center to consider, where the center just continues to go up by 1 each time. And then beyond that, we have the fact that you can rearrange these. You can always rearrange these, and you could consider these as squares. So we have the square numbers. Which of these is correct? All of these are correct. Which is the right pattern? They're all the right pattern. And they're all super useful to understand the approach, right? Because it's in this way that we start to see hidden truths that squares are connected to triangles, that triangles are connected to odd numbers, that odd numbers are connected to even numbers. This is something that drove people for thousands of years. And now you're starting to get a little insight into why people might have thought that numbers held religious significance and insight to the universe and its behaviors, right? This is why people study pure mathematics. This is cool. This is weird and unexpected and provoking. So let's talk, let's discover a formula here, a formula that we will use throughout this class. Let's imagine we are trying to capture how you add 1 plus 2 plus 3 plus all the way up till some number, just like Gauss was asked to do as a small child. We could try to find those patterned connections. That works out okay. The problem is then I need to really consider what I'm starting with. I need to really consider how it partners, where that middle number is. What if it doesn't work out cleanly? That can be a little challenging. What if we were to take a moment to step away from the algebra mindset and take a look at the geometry mindset? These could be represented as triangles. Triangles are nice, but they're not something that's easy to figure out the size of because they don't have that kind of flat hypotenuse. However, I do know that triangles relate to rectangles, my favorite shape, and are useful through that equation. So maybe we can use these triangles and we can partner them, we'll duplicate them and stack them against each other. Like this one here. I'm going to duplicate that 3 triangle and I'm going to stack it against itself to make a rectangle. I could do that for the next one too, right? I could stack this against itself so that I get a rectangle. And in this way, I could say that the pyramid, the little triangle that I'm looking for here is always going to be half of the rectangle I can form from doubling it, from duplicating it. Well, what are the dimensions? What's the size of that rectangle? Well, the size going up is always equal to whatever number is my highest, right? This was 2 as the highest. This was 1 as the highest. So I've got the size, whatever I'm counting up to is represented by the height. The width is always going to be that number plus 1. So it'd be the third would create a 3 by 4, and I would want half of that. The fourth would create a 4 by 5. I would want half of that. The second would create a 2 by 3. I would want half of that. So we get a formula here. We get a formula that if I can find the rectangle and the rectangle's dimensions are that n times n plus 1, because those are the dimensions, n by n plus 1, but I only want the triangle, then my formula would be find the area of the rectangle and then cut it in half. Because physically, that's what I wanted. Physically, that's what we're going for. And there you have it. This is a formula for the sum of all numbers between 1 and any endpoint you want to give. It's a rectangle. It's a hidden rectangle here. Here's an example that'll help kind of illustrate that with the number 5. So again, you can see for 5, we have 1 plus, here's 2 blocks, plus 3 blocks, plus 4 blocks, plus 5 blocks. So instead of going through and trying to count all the total blocks, we can just recognize it'll always make a rectangle. Those rectangles will always have a length that's 1 bigger than 5 and a height equal to 5. Or, said more generically, a length that is always equal to n plus 1 and a height that's always equal to n. So we get our first formula. Do me a favor in the chat, from 1 to 3, go ahead and throw me some feedback. How are we feeling on where this formula comes from, that it makes sense to us? I got a direct message from iPhone. iPhone, you're going to have to include your name if you would like me to be able to answer your question. So you can change your name by clicking on the top right of your little gray box, and then you would be able to click on rename. All right, I'm seeing lots of 2s, lots of 2.7s. Like, where do we have some questions? If so, throw those in the chat. Start to capture what those questions are, because I want this to be something that you can touch, that you can manipulate, that you understand what these formulas are. All right, I'll be looking out for questions as you throw them to me in the chat. Let's move on from there. Some people might ask, why do we need notation? Why do I have to introduce a whole new way of representing these patterns if this whole ... system seems to be working out quite well? So here is my question to you all. Here's an example. You all tell me, what's the pattern here? Think to yourselves on it. What's the pattern? I'll let you know. It's a pretty easy pattern to express once we know what it is. Think about it. What's the pattern here? This is a reminder that I've got a few people who responded in with that 1 to 3 poll, that who still don't have their names listed in their Zoom. So you need to make sure that you click on the 3 buttons on the top right of your thumbnail and type in, click on rename and add in your name. Otherwise, I cannot credit you for attendance because I just won't know who you are. All right, we've got cubes. 1 isn't a cube, though. Or sorry, 2 is not a cube. 1 is a cube. So 2 won't work as a cube. 9 wouldn't be a cube either, because I can't think of something times itself 3 times that makes 9. Now, the importance is not, I'm not looking for you all from like a specific answer here, but what I'm looking for is, can we all get on board with the fact that if I just give you a set of numbers, finding the pattern can be hard, right? That's what I'm trying to get us all to understand. It'd be nice if somebody would just tell me what the pattern is. Can we all get on board with that? Okay, that's the drive here. That's what we're trying to, that's why we introduced this notation, because we want somebody to know the pattern. We don't want them to have to figure it out again, right? Once we get it, let's communicate it, okay? So let's go ahead and take a look at this one. This one, by the way, the pattern here, it's just 1 bigger than the cube. You're super close, whoever said cube, super close, 1 bigger, right? So 1 is a cube number, 1 bigger would make us 2. 8 is a cube number, 1 bigger would make us 9. 27 is a cube number, 3 times 3 times 3. 1 bigger would make us 28. And so like this is a very easy like pattern to represent. We can represent this with some symbols, right? This is the pattern, 1 bigger than k cubed, that'd be k cubed plus 1. Like it's a very simple pattern if we know it. If we don't know it, it's incredibly difficult to determine. So what we'll put is we'll make a notation system that says, here's the pattern explicitly. There it is. That's the pattern we're going to follow. And then we'll say we're going to do an addition, a whole bunch of addition, a little summation. So to say that we're going to do addition and a summation, we'll use the Greek letter sigma. This is the Greek letter sigma. So sigma, the Greek letter sigma, comes from the fact that it's kind of the parallel letter to our Latin letter S. So our Latin letter S we use when we think of doing a sum. So this is a way of trying to show like, hey, it's a Greeks, like it's a sum. It's a sum, but I don't want to put an S there because we meant it's a Greek letter that we're assigning to represent S for sum. So that's what we're trying to play with here. So sigma just means I'm going to do addition. What about the k equals 1? This is where I'm going to be reaching out to anybody here who's got some programming experience, big fan of computer science. Like this is where you live. This is your home base, because you're going to think of this like a repeating program, like a for loop. It's going to say I'm going to start at k is 1. And then I'm going to repeat that pattern with k being 2, and then 3, and then 4. And I'm going to do this until I tell you to stop. So in that way, we see that I could expand this entire notation to say we're going to start with k equals 1. Here it goes. K equals 1 would be I put in 1, I cube it, I add 1. That's the first thing. Cool. Then I repeat that pattern with 2. So then I do 2 cubed plus 1, lock it in. Excellent. Those are the numbers in my pattern. What's happening between them? I look at sigma. Sigma says it's a sum. All right, so addition. Right? And then I do that again. It's the next thing in the pattern. 3 cubed plus 1, 4 cubed plus 1, 5 cubed plus 1. We're going to continue this going all the way until I get to the top. Wherever this thing is, then I'll stop. So if that n is 10, then I'll stop at 10 cubed plus 1. If it's 500, I'll go all the way until 500 cubed plus 1. It's just saying how long am I repeating this pattern for. Okay. So let's do an example here. So we've got, again, Euler. Euler can be credited for this notation system, right? We're going to hear about Euler when we start talking about E, that little 2.7-ish number. But for right now, Euler can get credited for this notation system. Let's try to decompress this one. The sum of every listed number between 1 and 10. Okay, let's try this out. I start with k equals 1. I plug it in. The pattern says, just tell me what k is. Got it. There's the k, 1. And then I find the next number. The next number says we're going to consider 2, right? The next number, so we plug in 2. Got it. What's happening between them? This is a summation, so we're going to add an addition symbol. Then I do with the next number, that'd be 3. And then what's happening between them? Addition symbol. And this continues until I get to 10. 10, I stop. 10's the highest. It tells me that's where I'm going to stop. I'm going to stop at 10. So we could go through the effort of typing in our calculator 1 plus 2 plus 3 plus 4, or we have a formula to help us with that, right? This is the triangular progression that we had explored before. I can solve this real easily. I'm going to make a rectangle that's 10 by 11 and recognize that I only want half of that. Well, 10 by 11 cut in half is going to be 55. Done. Quick, simple, straightforward. That's what we're talking about. All right, so I've got a question in the chat. Is there a reverse version of sigma? Don't think of sigma as something separate. It's not. It's just condensed addition. So if I say, what's the opposite of sigma? That's literally the same question as saying, what's the opposite of addition? Subtraction would be a great idea, right? But we're going to see an example where we can do subtraction with the sigma notation. So it's not about this being a completely opposite thing. Right now, the biggest hint I can give you, the biggest technique I can give you for this entire section is don't worry about this. Don't try to play with it. It's condensed, it's scary, it's new, it's difficult. My very first recommendation for any problem ever is list it. Decompress the notation, take it and stretch it off into something that you understand, and then use the tools that you already have. You don't need new tools for this. I'll give you a few formulas, sure. They'll help out occasionally, but for the most part, if you get stuck, break it out into something that you have. Addition, we've been practicing for years. Let's use that. We'll do some more examples. We'll help anchor this in. All right, what about this one here? So Ethan, this is going to go to your idea here. Where does the 11 come from? The 11 came from the fact that we were able to model this addition using that formula from before, where that formula said, this is a triangle. This forms a triangle as a shape, and a triangle is half of a rectangle whose dimensions would be n by n plus 1. If it's confusing where that came from, print off the guided notes, go back and take a look at it. Let's take a look at this one. We're looking for the sum of, what's this mean? Okay, first, let's not worry about let's just try to decompress it. I start with 150, and the pattern says I list it. Got it. There's 150. The next thing is I increment it by 1. I next do 151, and I list it. There's 151. I list it, because the pattern says just tell me what k is. Got it. What's happening between them? Addition. Fantastic. What do I do next? I go up to 152, 153, 154. I continue this way all the way until 277. So this is what we are playing with directly. Now, I don't want to type that in my calculator. That seems exhausting. Instead, we could look for a creative approach. Maybe a formula. I could reach for a formula, but the only formula I have at this point says if I start at 1 and I go all the way through it, then I can use that idea that it builds a triangle and builds a rectangle. I don't have 1 where I'm starting, unless I would like to make it that way. So let's just make it that way. All right, let's just make it that way. Instead, let's make it 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 all the way up to 277. Let's make it that way. Oh, but then that's not the same thing. because I've counted extra numbers. I've got 1 and 2 and 3 in there that I didn't used to have. So let's make a little note off to the side that I will also need to eventually take away the 1, the 2, the 3, all the way up through what? 149, right? I'll need to take those all away. Well, this is pretty cool. This is something that I have a formula for. This is that building of the triangle. This is that n by n plus 1 over 2. This is the 277 times 278 over 2. This is that formula. 277 times 278 over 2. What about this one over here? I don't have a whole bunch of subtraction, but I do see that it's the numbers 1 through 149. Maybe I could make this subtract 1 and 2 and 3 and 4 and all the way up through 149. Well, in that case, I have a formula for this, 1 through 149. That's going to be that rectangle whose dimensions are 149 by 150 split in half. 149 by 150 split in half is what I need to take away from it because I introduced those new numbers. So I could plug this in my calculator. I could do this so much more easily. I could practically do this by hand. Now, once we have this, like I want this to feel good. Like this feels good from a we get it level, not like a mystery formula level. Like we get this because it makes sense. Because once you get it and it makes sense to you, then we can bring in the notation. Then we can bring in the more formal notation. Then we can bring in all of this because take a look. Now, if I write it like this, it makes sense. The numbers between 150 and 277, if I add them together, is the same thing as adding all the numbers from 1 to 277 and then taking away all the numbers between 1 and 149. Right? Because I added all the way up to 277, but I really wanted to start at 150, so I need to take all those earlier numbers away. So we can write it this way. We can use condensed notation. But you don't have to. It's not a need. It's not even better. It just saves you some pencil lead. Like it's not that much of time savings, and it's certainly better than like using it wrong and getting the wrong answer. So if you understand it, feel free to use it. If you don't understand it, work your way up to it, but always insist that you bring it back to something you fully understand. It will get you the same place, and it's not going to take that much longer. So build up to it. Don't force this. This is not a thing to force. In the same way that earlier when we were learning multiplication, right, as children, to just be like, memorize your times tables would have not been an efficient strategy of learning. Eventually, we just got really good at kind of knowing where that answer is because we had done practice problems with it enough times that we began to recognize common solutions, and then we had it, right? So don't just force people to memorize a brand new thing. Build it on something you already know. It's how our brains are built. All right, let's find another cool example. What about this one? Let's do the sum of all squares. The sum of all squares. So I'm going to do 1 squared plus 2 squared plus 3 squared plus 4 squared. I'm going to add squares together. Well, we might recognize I can take that geometrically. I can make a pyramid. So here we go. This one block on the top, this represents 1. I have 1 block on the top. Underneath it, I'm going to stack 4 blocks. 4 blocks. And then below that, I'm going to stack another square of 9 blocks. So what I'm creating is I'm creating a pyramid, sort of a lopsided pyramid here, where I could continue this pattern forever longer, where I'm just adding squares underneath the pyramid. Okay, so I've got a representation, a geometric representation of adding squares. Well, similar to our other motivation, triangles and pyramids are hard. Let's try rectangles. Or more creatively, what about a 3D rectangle? We'll call it a box. So we could make a box out of this. We could repeat the pyramid 3 times and notice that it's going to nest in against itself quite nicely, almost perfectly, except that on the top here, we're going to have a little bit of overhang. A little bit of overhang. So finding the dimensions of this box is going to be a little bit difficult because it's not a box yet. I have a solution. I will go to the hardware store. I will buy a saw. I will cut this thing in half and I will flip it. I will flip it so that it nests nicely. Now it will be level. So I've got that shaded in the next one. So we can see it's shaded. I've cut it into 2 different pieces. I flip it on over. And in that way, now I have a nice dimensional box. That dimensional box will always be the case because it's built on 3 of those pyramids. So what that means is that if I can always make this box with 3 of those pyramids, and its dimensions are n by n plus 1 by n plus a half from the time that we split that little top bit. And I want one of these pyramids, because that's what I started with, was one pyramid, then I'm looking for 1/3 of that size. 1/3 of the box. And that's where we get our formula for. If you take a look into a calculus textbook, you might see a slightly different formula for how to solve this. I promise you they are equal. They are equal. One is just a simplified version. But I like this one because this one I can remember from a picture. This one I can remember from a picture and a story. I'm just making a box. N by n plus 1 because it's a nesting up against, and then n plus a half because it was a nesting against that I needed to make flat. N by n plus 1 by n plus a half divided by 3. So let's do an example here. We're going to, again, decompress this. No need to stress. So let's try to decompress this. First, we're just going to decode it. Always great to start by decoding it. We're going to start by 1 because it tells me to start at 1. So I list 1 and then plus 1 squared, right? That's the pattern. The pattern says take the number and add it to its square. Got it. List it, then go on to k equals 2. So k equals 2 would be 2 plus 2 squared. That's the second thing in the pattern. What's happening between them? A summation. And then I'm going to continue this all the way on down until I get to that top place where it tells me to stop. That's going to be 27. So I get 27 plus 27 squared as my last thing added. Once this is written out, notice that we don't have to keep the parentheses. The parentheses serve no purpose. There's just a bunch of addition happening here. So I could drop the parentheses. I could go through this entire thing and I could erase the parentheses. All right, so this is fine after I list it all out. And then on top of that, this is a bunch of addition. We've already explored that addition has a commutative property. The fact that I can move it around, these are just piles in a sandbox. I can move piles and I haven't changed the meaning of the quantity in the sandbox. I could take this and I could rewrite this. I could do 1 plus 2 plus 3 plus 4 plus 27 all the way up, right? And then I could group that with the other squares. I can make this 1 squared plus 2 squared plus 3 squared all the way up to 27 squared. Well, this is something we have a formula for. This is adding up of everything between 1 and 27. I know how to do that. That's going to make a rectangle with dimensions 27 by 28, where I only care about half of it. And this one I have a formula for. This is the sum of all those squares up through 27. This is something I have a formula for. This is going to be a box whose dimensions are going to be 27 by 28 by 27 and a half, where I only care about 1/3 of it. So there's our summation. But it's only after we understand where these come from that we see an ability, a shortcut, if you will, that we can make sense out of. We could have started with assigning the summation separately. Because that's what we had down here. This right here is the sum of all of those k values between k equals 1 and 27. And the other one was the sum of all the squares from k equals 1 to 27. So it's okay. It logically makes sense that if all I'm doing is addition and addition of addition, that I should be able to do addition of addition in whatever order of addition I want to do for addition's sake. So like, again, don't fight for these formulas. Don't fight for these rules. There's zero need at all. If you end up finding a shortcut and you logically understand that it has to work every time, feel free to use it. Feel free. But if you start putting in shortcuts in places where you have not understood the full logic, you might get into a difficulty because you'll start trying to solve things in a simpler way and you'll change the meaning and you won't realize it. Because until you know what it means, there's no way to double check your work. You got to start with the meaning. All right. Here's a last one. We could do a sum of cubes. I'm not going to go through exactly the proof that allows this to be true, but it is in the guided notes. And I'd recommend you take a look at it because it uses the area model. It uses the rectangle that I showed you last time. It uses the rectangle in a fantastically creative way. And I've got it listed in the guided notes. You can take a look. But what we can see from a conceptual standpoint is that if we have these sort of ever-growing Rubik's cubes to consider, that you can unroll those Rubik's cubes in just a way that makes them into a larger and larger square. So that adding up of 1 cubed and 2 cubed and 3 cubed and 4 cubed is actually the same total number of Rubik's Cube blocks as making a square whose dimensions are 1 plus 2 plus 3 plus 4. Because I would unroll it sort of in that nice little angle pattern. Well, that's interesting because I have a formula for that. I have a formula for what happens if I add 1 through a number. We already know that one. That's going to be n times n plus 1 over 2. So n times n plus 1 over 2 is the sum of all of the counting numbers. So if all I'm doing is using that as a square, then there's my new formula. The sum of the cubes comes from the sum of all the counting numbers made into a square. So sometimes we'll simplify that, and you might see it written in textbooks where it's written like this: n squared times n plus 1 squared over 4. But I don't use that one. I use this one. Less to remember, right? Now I only have to memorize one formula, possibly 2 formulas, both of which have storylines and pictures I can use to fall back on. Right? Easy. So again, we can compress this notation if we want. The sum of all numbers between k equals 1 and n of k cubed equals this formula. You can see the formula, it's fine, but you don't have to have it. So we've got all of these different things, but don't take away from this that there are formulas. Take away from this that there are creative approaches to make formulas, that there are stories, that all of these should feel like they were within your grasp. Like you could have found these. If you were given sufficient motivation, sufficient time, and sufficient preparation, you could have landed on these formulas, right? They should not feel like they just simply came out of the ether. They're just creative approaches. That's all they are. So next class, what we're going to talk about, where did pi come from? We know that pi is a forever long number, but I don't know of anybody who's figured out how to measure forever yet. So how did that happen? Why do we call things square inches, miles, kilometers? Why are they all squared? Why not measure things in triangles? Why not measure things in circles, rectangles? Interesting questions. And lastly, how many square inches is your handprint? We know that our hands are smaller than a foot by foot square, so it must not be quite a square foot, but it's also bigger than a square inch. So where is it in between? How do we measure that? How do we measure curvy objects in general if I don't have a formula? These are all interesting questions.